I don't think.
Are all of our presentations on your computer, Dimitri?
Huh?
Are these all the presentations that we sent you today?
Well,
I
have your
notes.
down
Huh?
yours.
I have a presentation from last week, and I have the one that you sent today by 6 slides. Are they identical? Thanks.
The 6 slides is identical to today's.
To what was yesterday?
Last week's isn't the same.
Let me do something. Yeah, slides there.
I've seen this one quite a few times. So if you want to write down on it. Yes, this was last week's. Whenever I was here.
No, it builds a recursion.
Yeah, what the heck?
Oh, it's a little different from what we want, but it's... we will since I'm presenting.
You can say, make this screen the only one. I think. I think it's up at the top by pause
and show, use slideshow, tips.
No, or try the one in the middle.
Thank you for the tip. You can use the original computer later. Well, if you ever get here again. I was gonna say I had notes on here. I was gonna look at it by myself, but I guess I'll try to go from memory. So, we ready? Always ready. So, hello everyone. Today I'll be speaking to you all about a case study of dye-sensitized lead-halide perovskite solar cells, where we explore the dye morphology influence on hole transfer. So we look at spatial locality of the dye versus explicit ligand coordination, or in simpler terms, we're looking at through space or through bond hole transfer. So here we're modeling two competing processes that occur in charge transfer, where we compare through space charge transfer and through bond charge transfer of a hole, which is donated from the perovskite and donated to the dye molecule. And these two illustrations here show that a dye molecule, this would represent the through space charge transfer because there's no electron density in the middle for bonds. And on the right, we look at through bond charge transfer, where we have electron density of bridging between the dye and the perovskite. And the important thing to know is for the models that we're going to look at, that the through bond pathway is much, much greater than the through space charge transfer rate. So here we'll look more in depth at the atomistic models that we're going to look at for the rest of the presentation. So lead-halide perovskite models, the dye models that we used, and then the combination of the two of the system. So generally the work that we looked at for these projects, we probed the dimensionality of the perovskite material, where each of them is a cesium-lead-iodide based perovskite. And we look at a nanoparticle, which is still computing, we don't have results for yet, cesium-lead-iodide nanowire and thin film. And we look at the different dimensionalities because they each provide their own unique benefits. So with a decreased amount of dimensionality, you get increased interfacial surface area. And that's helpful because charge transfer for these systems is limited by surface area. So more surface area, you can get greater yields. And you also expect greater coupling as well with decreased size due to increased surface energy. But for this presentation today, we're just going to look at the thin film model because it's, I guess it provides the best comparison to experiment for the results that we have. So for the dyes that we use in practical perovskite-based solar cells, normally Spiro-MeOTAD, an organic molecule, is used as the hole transfer material because it's shown to be the most efficient hole transport material in these systems. So as you can see on the left, it's a rather large molecule. So to save computational expenses, we made an approximation where we basically just cut it into a segment or a fourth of the whole Spiro-MeOTAD molecule, as you can see on the right. And then we also do a control experiment without the methoxy linker groups because we suspect that hole transfer, that the methoxy linker groups play a vital role for fast hole transfer. And then here we show the smallest repeating unit of the cells of the models that we use without periodic boundary condition shown. So on the left would be a through space modeling charge transfer or hole transfer, where the dye molecule is arranged vertically or normal above the perovskite surface. And then on the right would be a through bond model charge transfer, where the methoxy linker groups are explicitly coordinated to the surface of the perovskite to the iodines. And then the thing to note between these, we can consider these as like in a physical experiment as limited cases between the two. So for the through space, it would be a case of minimal interaction between the dye and the perovskite, because since it's normal, it doesn't get any of the pi stacking interactions with the surface of the perovskite. So it has minimal interaction and it's quite far from the surface. Whereas for the through bond space, you could think of it as a maximal case of strong interaction between the dye and the perovskite. So we would expect that our rates would reflect that, where the through space would be longer than the through bond. So for this slide, we're going to describe how we define charge transfer and the physical processes that occur for the hole transfer to occur. So on the left is an illustration of the hole transfer occurring in the perovskite dye model. So the left bars show the energy or band structure of the perovskite material, and the right the dye or the dye with methoxy linker groups. So we can see that first the perovskite is going to absorb light with an energy h mu, and it's going to create a photoexcited electron hole pair, where the electron occupies a state luma plus y and the hole HOMO plus x. And after a certain amount of time, that the hole or the electron is going to thermalize to the luma of the perovskite, and that the hole is going to thermalize to the HOMO of the dye and the DML. Since that would make they'd both be in equilibrium in that case. So the thing to remember is that we're going to define the HOMO of the dye and the DML as a successful hole transfer state, since that's where we expect the dye to show up after complete thermalization. And then we're not considering any hot hole transfers in this case. So we're losing all the energy above the band gap. So all excess energy is lost to thermalization. And this slide is just to characterize the hole transfer states. So on the right, we see the density of states for both of the models. And we can see clearly that, or I guess I should explain more depth. So the electron density is partitioned between the electronic states of the dye and the perovskite, where the red is the perovskite and the blue are the dye states. And then bold or filled in states represent occupied states, and then the blank states represent unoccupied electronic states. And we can see that for both of the models that the HOMO of the dye is significantly greater than the thin film, so we'd expect that the highest occupied orbital of the system would be occupied on the dye, which we can see in the two figures on the left, where the green blobs indicate the molecular orbitals are occupied on both the dye and both systems. So now we get into the exciting part of this presentation, where we look at the electron dynamics that occur in these systems. So we use red field theory and density matrix formalism, where we expand the density matrix up to second order perturbation, where we view the ionic interactions with the electronic states as a perturbative interaction. And then, this is why I had my notes. Can't remember what I was going to say next. So,
I don't know how to make it go back.
it's just a button, but
Right there.
Use present review. Click. Oh,
Yeah,
no,
you
same.
probably-
Click, hold, move to the right.
Okay.
I don't think I'm clicking right.
Click, hold, see, use present review.
Oh, you're not a Mac guy, are you?
Yep.
There you go.
Oh, there we go. Okay, so then, second order. So then, yeah, there are two terms that contribute to the time evolution of the density matrix. So the first term would be the unitary time evolution of electronic stage, which is generalized as the Louisville-von Neumann superoperator. And the second term is a dissipative term, which describes the energy loss from the electronic system to the heat bath, which is generalized as the Redfield superoperator. So then these two operators, they represent a solution to the density matrix at each increment and during the molecular trajectory. So then, if we solve for the density matrix in each system, we use the above two figures to characterize that the solutions of the density matrix for each step in the trajectory. So I guess I can go back now. So the above left figure shows the energy occupations for each time in the trajectory. So on the x-axis is log time, so 0 would represent 1 picosecond, -3 would be a femtosecond, 3 would be a nanosecond, and so on and so forth. Then the y-axis is the energy. So then the yellow represents gains in electron density during time. Blue would be loss of electron density in time, so essentially a whole state since we're losing an electron. And then the background green is just the ground state equilibrium electronic energy. So we have a photoexcitation from HOMO minus X up to LUMA minus Y, and we track the expectation values of the energy at each time, which is represented as delta epsilon H in the equations below. And after a certain amount of time, the expectation values will dissipate to the HOMO and the LUMA. So we calculate the expectation values up to that point. And then assuming that we have a single exponential decay, we set the regular exponential form equal to our dimensionless energy, which is capital E sub h. And then we solve for the rate constant K sub h. And then that's what we defined as our whole transfer rate from the decay from HOMO minus X to HOMO. And in the case of multi-exponential decay, which we see in this figure, we just take the 1 over the sum of the lifetimes for each state. And then on the right-hand side shows the time evolution of electronic states, electronic occupations in state and, well, regular space. So basically projections of orbitals onto the z-axis. So again, the yellow represents increase in electron, or gain in electron density. Blue represents whole states, and the background green is just the ground state charge density. And the figure right next to that just explicitly shows that the projections onto the perovskite dye system, where each of the dotted lines just show that's where we expect higher concentrations of electron density. So on this slide, we characterize the hot hole relaxation for the most probable excitations for both systems. So for the perovskite dye model, that's from HOMO minus 2 to LUMA plus 10, and for the perovskite DML system, it's from HOMO minus 10 to LUMA plus 5. And below both of those shows the corresponding density of states for each system. Then the figure on the left shows what you'd think of as a more conventional rate to express the rates and lifetimes for each transition. So one thing to notice about both of the systems is that they both show multi-exponential whole decay, and we can attribute that to the subgap between the HOMO of the perovskite and the HOMO of the dye. As you can see in the density of states figures, they both have a substantial subgap of 0.72 eV and 0.81 eV, respectively. And if we consider the non-adiabatic coupling term, which describes the the mixing of electronic states due to the ionic motions of the systems, and then the Fermi, I suppose I can move it out of the way so we can see it. And then the Fermi golden rule, which characterizes the transition rates between two electronic states, we can see that the non-adiabatic coupling term we could show using the Hellman-Feynman theorem that's proportional to the inverse of the gap between the two states. So for states lower in the valence band, it's essentially a continuous energy spectrum. So we'd have a small denominator will give us a high coupling term. So you'd expect fast transitions between those states. But between the HOMO minus 1 and HOMO states, there's a big subgap, so we have a big denominator, small non-adiabatic coupling term. So we'd expect longer or slower rates between those states and longer lifetimes. So that's what we attribute these subgaps between KH1 and KH2 for both of these systems, is to the subgaps between the HOMO and HOMOS minus 1 state. But then even between those, if you look on the figures on the left, we'll see that there's a pretty significant difference between the whole transfer rates between them. So we can see for the first transition from the HOMO minus X to HOMOS minus 1 state, we see that for the thin film dye system, it takes about 10 picoseconds for it to occur in the through space model, but for the through bond model, it's about 2 picoseconds. So there's an order of magnitude difference between them, but nothing really significant or too dramatic. But we can see for the HOMO minus 1 to the HOMO state, the through space charge transfer has a nanosecond whole transfer rate, but we still get quick picosecond resolved rates for the through bond system. So the big takeaway here is that nanoseconds is a lot bigger than picoseconds for through space versus through bond. So why is that? Why is a through space much longer than through bond transitions in these systems for non-adiabatic transitions? Well, if you consider the molecular orbitals, or the orbitals that participate in these charge transfer reactions, so for the HOMO, so we have two figures showing on the left the thin film dye system and the orbitals that participate, and on the right the through bond pathway through the linker, the orbitals that participate. So if we look at the through space model first, we see that from HOMO minus 2 to HOMOS minus 1, the orbitals are located on the surface of the perovskite, so they're going to have decent overlap with one another, which gives about a 10 picosecond transition rate. Oh, I should probably mention that our rate law from our Fermi golden rule, and its rates are strictly proportional to the overlap of the orbitals. So we want small overlap, small rate, big overlap, big rates, or fast rates.
And that's in time, right?
So these would be rates.
No, but is it?
So it's like 1 over time.
Time of the nth orbital and the jth time of the kth orbital. So they're the same time, or are they time steps different? It's hard to see from back here.
I guess.
It doesn't look like you have any dependency on time.
Can I quickly help?
Yeah.
Formally, it is comparison of orbitals at different time steps. But intuitively, very roughly, if the orbitals do not occupy the same area in space, then the rest, how far they are in time.
So for our bonded system, the HOMO minus 10, so for our HOMO minus 10 to HOMO minus 1 transition, and then HOMO minus 1 to HOMO. HOMO minus 10 and HOMO minus 5, they're just all located on the perovskite, so I didn't show them. But then once we get to HOMO minus 4, HOMO minus 3, we start to see the effect of the bonding. We'd expect there to be electron density in between, like located in between the linker group and the perovskite, which we see here. So intuitively, we get the expectation that we resolve. And then from the HOMO minus 2 to HOMOS minus 1 states, we get electron density on the linker groups and the corresponding benzene rings. So due to this orbital occupation on the HOMO minus 4 and HOMO minus 3 state, we get good overlap between these two transitions, which give a picosecond transition lifetime. And then from the HOMO minus 1 to HOMO minus 2 to HOMO, we get a good overlap due to the orbitals on the linker group and the benzene ring. And then here's just on the dye molecule itself. So we get decent overlap between these two states. So yeah, we can attribute the long difference in the charge transfer rates of these through space through bond due to the orbital overlaps in these systems, where the bond provides a linking, like a bridging orbital density. And then I forgot to put my sources on here, but so how does this correspond to experimental hold or experimentally determined ejection rates in these systems? So there's a wide variety that have been reported in the literature, which span from approximately 1 picosecond to the max value of 16 nanoseconds. So comparing the results that we have, just to refresh people's memory. So we get, lifetimes of about up to nanoseconds, and for the through space models, and then for the through bond models, we get up to picoseconds to 10 picoseconds. So it seems like our computations kind of cover the two limiting cases of very rough or poorly interacting systems taking long transition rates up to nanoseconds, and then well interacting systems which are very fast and happen on the scale of picoseconds. So our hypothesis from this work is that the through space pathway corresponds to nanosecond hole injection, and the through bond is to fast picosecond hole injection. So just to recap the work that we did, we examined two cases of maximal and minimal interactions of a Spiro-MeOTAD segment with the lead-halide perovskite thin film. And we found that the energy offset between the HOMO of the perovskite and the HOMO of the dye delays hole transfer initially, because it takes a long time for the charges to overcome the energy barrier. And then we also find that the through space pathway has minimal orbital overlap, which decays non-adiabatic transitions. It gives us a magnitude of nanoseconds lifetimes. And then the through bond pathway provides bridging electron density to overcome the energy offset to provide fast picosecond hole transfer. And then the time scales that we compute correspond favorably to the upper and lower bounds of experimentally determined hole transfer rates. So that is my conclusion. And I have to put on a...
Okay, let's thank